Greetings everybody. This video will hopefully explain, uh, is from chapter 10, Newton's second law for rotation. And so what we do, and it has to do of course with an object that's rotating about some axis or about some pivot. And what we do is we start with the linear, and remember when we say translational, translational and linear mean the same thing. So let's start with the linear form of Newton's second law. The sum of the forces acting on an object equals ma. And what we're going to do is we're going to replace force with torque, mass with moment of inertia, and linear acceleration, a, with angular acceleration, alpha. And so instead of the sum of the forces equals ma, we have the sum of the torques equals I alpha. And that's Newton's second law for rotation. Now remember, when we talk about the torque, that an object is rotating about some axis or about some pivot. Well, let's look at this first example. And here we have a uniform rod of length L, mass M, and at one end it's attached to a frictionless pivot. And it's free to rotate about the pivot in the vertical plane. In other words, when you release the rod from rest, the weight of the rod, which acts at the cm of the rod, the weight of the rod will pull it down, and hence the rod will rotate about that pivot. So the weight of the rod, mg, is exerting a torque on the rod, because that mg is the force that's causing the uniform rod to rotate about the pivot. So when we talk about the torque, mg is creating the torque. And I want to know what is the angular acceleration of the rod, and I want to know the initial translational acceleration of the right end. So I want to know alpha and at. And remember, alpha is the same everywhere on the rod, no matter, in other words, any point on the rod, no matter where they're located relative to the pivot. It could be a point on the right end, a point, here, a point in the middle, a point over here. Every point on the rod will have the same alpha. The tangential acceleration, at, that depends on the distance from the pivot. Different points on the rod, because they're located at different distances from the pivot, they will have different tangential accelerations. Okay, well, let's apply Newton's second law for rotation. The sum of the torques equals I alpha. Well, now remember, what is torque? In general, torque is Rf sine theta, where R is the lever arm, F is the force, and theta is the angle between the force and the lever arm. And remember, I want the initial angular acceleration. At the instant the rod is released, what is alpha, and then what is the at of the right end? Well, so the torque, the force is mg. Clearly it makes an angle of 90 degrees with the lever arm. The lever arm is indicated by this black arrow. And that lever arm is a distance of L over 2, because the weight of the rod acts at its cm, which is right at the center of the rod. So the torque is, so the force is mg, and the lever arm is L over 2, and it's sine 90, because I want the initial angular acceleration. At the instant the rod is released, mg and the lever arm, they're at 90 degrees. So you get mg L over 2. Now remember, I alpha. Well, I is the moment of inertia of a uniform rod pivoted about one end. If you're not sure, table right here. Uniform rod pivoted about one end. The moment of inertia is 1/3 ml squared. So sum of the torques equals I alpha. So mgl over 2, that's the torque. I is 1/3 ml squared, and then alpha. That's Newton's second law for rotation. Now solve for alpha. Well, the m's cancel, and you get alpha is equal to 3g over 2l. Now I want the tangential acceleration of the right end of the rod. Well, remember, let me pause it for a second. Well, remember that the tangential acceleration is r times alpha. Well, remember, r is simply and remember, every point on the rod will have the same alpha but a different AT. And R is the distance, in this equation, R is the distance from the point on the rod to the pivot. That's the definition of R. It's the point on the object. R is the distance from the point on the object to the pivot. So obviously AT is going to be different depending upon the location. But remember, every point on the rod has the same alpha. So in general, AT is R times alpha. Well, in this case, the right end of the rod, the distance, it's at a distance of R equal to L from the pivot. Remember, I want AT, the tangential acceleration of the right end of the rod. The right end of the rod is at a distance L from the pivot. So AT is, in general, AT is R times alpha. So AT, what is R? R is L. What is alpha? 3G over 2L. Okay? So you get AT is equal to 3 halves G. Notice it's actually greater than the tangential acceleration of the right end of the rod. It's 3 halves G. It's greater than G. It's sort of interesting. There's a common, you can Google, I should have embedded it in the lecture, but there's, you can Google a video on YouTube, where you take this case, you have a uniform rod pivoted about one end, and you stack like a couple of coins on one end, like 2 or 3 pennies or nickels or whatever, and then the rod's released from rest. And what will happen is, because the right end of the rod accelerates at a rate that's greater than G, the right end of the rod will fall faster than the coins that are stacked up on the right end. And it's a good common YouTube video, you can Google it. And it's because once you release the rod, the right end accelerates at 3 halves G. But the coins, once the rod is released, they're in free fall. They accelerate at G. So the right end accelerates faster. It will actually fall, and you'll see a gap appear between the right end of the rod and the coins that are on there. But again, that's the idea, is that every point on the rod will have the same alpha, but AT, the tangential acceleration, that depends on R. And by definition, R is the distance from the point on the rod to the pivot. So the right end of the rod, that distance is L. The right end of the rod, that point is the distance of L from the pivot. So AT is L times alpha. What is alpha? 3G over 2L. The L's cancel, you get 3 halves G. All right, let me go ahead and, now the next example I'll put in another video. It's a very common problem. There's one like this on exam 4 and on the final, where you combine Newton's second law for rotation and Newton's second law in the y direction. What happens here is we have a mass on a string, and the string is wound around the cylinder. And when the mass is released, the mass falls, and the cylinder is pivoted about an axis through its center. So the cylinder, when the mass falls, it causes the cylinder to rotate. So we apply Newton's second law in the y direction for the falling mass, and we apply Newton's second law for rotation to the rotating cylinder. The cylinder is pivoted about an axis through its center, through its CM. But I'll put that in another video. But it's a combination of Newton's second law for rotation applied to the rotating disk, and Newton's second law in the y direction applied to the falling mass. But I'll do that in a separate video. Alrighty, let me go ahead and get this video posted.